All right. So there have been a few extra examples on the regression notes that you need to read on your own, but I don't think there's anything really new. There's a very nice regression example, I think, at the end with the evidence approximation. I strongly recommend that you do it. And you look at the computer program because it's only very few lines, but it does very nice model selection and everything you need to know. So I just don't feel the need to do micro details in an audience of 6 because they may be coming from one ear, getting out on the other. So, we try to do only the very substantive things. So with that said, I am going to jump to discuss a little bit about classification. I'm going to try to make connections with regression and linear models, but you will see things are a little bit different. And maybe in the lecture tomorrow and on Thursday, you will realize in some ways classification can be a more difficult task than regression. Okay. So let me define what the problem is. Lots of these things are already familiar to most of you, but it's good to set the notation forward. So we're going to assume that we have some vectors x, if my pointer works, there it is, okay, and x is in d dimensions. So we're not working in 2 or 3 dimensions. X can be 1,000-dimensional, and we want to assign it to one of capital K classes, CK. So you can imagine the data come maybe from different sources, and in this particular case, I'm assuming that they have K different sources, so K different classes. In actually all these lectures, the handout, this capital K is going to be assumed known. Okay? The interesting problem actually is when you make capital K also known. Okay? And maybe one of you will be interested to read more about this because it's a more relevant research topic, but we're assuming we're going to assign this d-dimensional vectors to capital K classes that I denote here with CK. So obviously you can imagine this, training points in d-dimensional space. Eventually we're going to have to separate them, right? And say the points there is class C1, the points there is class C2. And the way we separate them is using what is called these decision boundaries. And the regions they define are what's called the decision regions. Now, in many occasions, we will be interested to see simple models where these decision boundaries are d-1 hyperplanes embedded in the d-dimensional space. So you can imagine in 3 dimensions, you put a plane and you say it separates class 1 and class 2. Okay? So it would be nice to somehow see if we can come up with some models that have these d-1 hyperplanes that separate the different classes. So if I give you a number of data sets, right, and you manage to actually separate them with these linear decision boundaries, then the data are called linearly separable. So I want you to remember this. So at points that you can separate them with planes, they're linearly separable. In many occasions, if, and we will see examples, you may not be able to do this, and you may need to have curved boundaries, right, to do this. But this is always, you will see the buzzword, linearly separable data sets. All right. We're going to start actually with very simple things today in the notation. So let's say that if we have, so we have a number of training data sets. So we're going to use the same way we did for regression, and I gave you input and output. My output here would be what class, let's say, a given training point belongs. And for a 2-class model, I'm going to use as a target t equal to 1 to denote class C1 and t equal to 0 to denote class C2. Now, for some algorithms, just a warning, the labels may be 1 and -1. And there is a reason for that. But right now, it's 1 and 0. Okay? As a matter of fact, I want you to think of 1 and 0 being sort of probabilities, right? So when you say this belongs to class 1, it's like saying the probability, it is the probability of that point x being in class 1. Okay? And now, if somehow you have, let's say, 5 different classes, you can think of a target vector that looks like this, all right? So this particular point belongs to class 2. Now, later on, I may not give you things like a target vector that is 0, 1, 0, 0, 0. I may give you 0.1, 0.3, 0.5, where the sum of this is equal to 1. So in some sense, in those cases, what I'm going to do is I'm going to do soft assignments to classes. So I'm going to say this point is a little bit in this class, a little bit in that class, and a little bit in that class. But right now, in what we do for the training data sets, right, we're assuming we know the exact target. So in this particular case, this point is in class 2. Okay? But obviously, remember, the sum of these numbers is equal to 1. Okay? And the assignment here is hard. It says, the probability can only be 1 or 0 for a given class. All right. This slide is extremely important, and the sort of the literature in this area is very confusing even to me, since I don't really care enormously about classification. But the literature, sometimes people, they introduce terminology without thinking, and then it sticks, and we cannot change it because it's written in the books, okay? So I want to give you the essence of the different methods for doing classification, and I want you, when you read something, not to extrapolate from the name of the method, but what the method does. You can say, I understand this is what this does, and this is what that does, but don't pay attention to the fine detailed names because maybe, maybe misleading. All right, so we're going to have multiple cases. I'm going to start with the case 1, where somehow we're going to introduce a function that is called a discriminant function that directly assigns a point to a class. So I have a function that, let's say, if it is positive for that given x, then I have class 1. If it is negative, then it's class 0. All right? So that case, no probabilities or anything, you define a discriminant function that obviously you're going to have to fine-tune it, so we have some coefficients that we have to compute, but you do a direct assignment to the class given x. There's no probability rules, there's no Bayes rule, nothing of this. A function that directly assigns an x to a specific class. Okay? And then this second cases, we're going to try to work a little bit with probabilities. And we're going to do the following. Case A, we're going to try to model directly the probability that x belongs to class CK. Right? This is what we want to know, right? If I give you an x, what class does it belong? So we're going to try to model this directly, which means I am going to postulate some form for that probability in terms of some parameters, and then you will calibrate those coefficients, using your training data. But somehow you're going to directly model this. No Bayes rule, no nothing. Okay? So in some sense, this case 1 and case 2a, they're close to each other. The difference is there is no probabilities involved there. Here you're actually modeling this probability. But you can say, if you call this some function of x, maybe that's your discriminant function. All right, so there is some relation between the two. Okay, and the last case, which is extremely important, is a generative model where somehow you will still make decisions using that probability, but you will calculate this probability using Bayes rule, and that requires to have some prior on the class labels on CK, and also for each class to know what's the distribution of the data coming from that class. Can you see the difference? So this last case requires that for this class the data come from this Gaussian, from that class from another Gaussian, for the third class maybe from a mixture of Gaussians. All right? So you need to know this class conditional probability, and obviously you need to know the priors, and then he will use Bayes' rule to directly compute that. So what you will be actually computing, the unknown parameters, most probably will be parameters that come in this conditional class probability, and maybe on the priors as well. Now, you may say, but at the end of the day, if I call the whole thing some function that I get, isn't it the same as that? No, it is not the same, because effectively, this model is generative. And what generative means, if you actually want to generate more data coming from class C1, you can do that. Why you can do this? Because you already have this distribution. The other models, you have no idea about the generation of the data. This model, you can actually say, I can generate more data from class C1, more data from class C2, right? And you can do different tasks using this data. That's why we call this model a generative model. So I repeat again the three classes, right? So things don't get confused in the next few lectures. In the first case, we're going to come up with some function that directly says, if this function is greater than 0, assign it to this class. If not, assign it to that. That's a discriminant function, no probabilities involved. In the other cases, we're going to actually compute probabilities. That's the probability that x belongs to class CK. In one case, we're going to compute this directly. So we're going to approximate with some form, some function of x, what this is going to look like. And in the second case, we're going to use a generative model that requires to have the class conditional probabilities that will allow you to generate more data similar to the ones that we have observed. Okay. All right. So I'm going to start, I notice in the slides, different things are mixed up, especially when you try to compare different methods. So I may be showing you pictures that compare the method that I discussed with other methods that I have not discussed yet. So you are going to see actually the same picture maybe 2 or 3 times every time a different method comes to play a role. So I'm going to have to throw you some ideas on things that we will discuss later. Okay? So so at least you hear multiple times what is going on. Okay. So we said we are in the first model, right? We're going to have some discriminant function, all right, that depending on what value it takes, we will decide what class we are. So what type of function of x that can be? And here is a very simple way to say, look, I'm going to take some linear transformation of x, W transpose x plus some bias term. That sounds very familiar for regression. And then I'm going to take some nonlinear function f. Okay? And a typical function, actually, we will see will be the sigmoid function. Okay? We will see pictures of that. So y of x is going to be some function of W transpose x plus W0. So you can actually see immediately the difference from the models for regression that we did is this model, you remember in the regression we call the models linear models of regression, and I emphasize the word linear means linear in what variable?
Basis function. Basis function.
Nope. The basis functions in W. All right? So linear in W. But now you can see for regression, for classification, because this function can be a sigmoid, for example, this function is not linear function in W, which actually means that trying to actually compute what W is going to be for classification for this model is going to be a little bit more difficult. Okay, because there is a nonlinear function. So this is a nonlinear function of W. However, the decision boundaries that will separate classes are linear functions in x and W. Can you see that? So a decision, let's say that you say if y is positive, you have this class. If y is negative, you have this class, right? So y equal to 0 is what separates two classes, or in general, y equal to constant is what defines the boundary between two classes, and y of x equal to constant means w transpose of x plus w0 equal to constant, so the decision boundaries are linear, which is nice, right? So you have these linear hyperplanes, right? D minus 1 dimensional embedded in the d-dimensional space. So again, for this type of function that we would use for classification, the function is not linear in W. The separation boundaries are linear in W and in X. And these models, by the way, you will see actually maybe in the last 3 or 4 slides of this handout from the lecture today that we will do next week. There is a generalization both for regression and classification for these models, and all of this go under the name generalized linear models. So in a different environment, somebody will actually ask you to go and take a whole course on generalized linear models. So the whole course, we will cover it basically in 10 minutes when we reach that point. But they go under the name generalized linear models because they're very powerful. Okay. Now, obviously, you remember when we did regression, instead of x, somebody can say, can I actually put phi of x there? And the answer is yes. Actually, you know, if you want, you can put phi of x, okay? But then, can you appreciate that the decision boundaries, they are not anymore, planes in the original space, because they would be planes where, in what space? If I put a phi of x there, the separation boundaries will be hyperplanes on what space?
The future space?
In the future space, right? So we have x, we transform into phi of x, so in the future space will be planes, but not in the original space. So when you try to plot something, it may look, a plane on phi of x, but when you see it in the real space, you actually get something more complex. Okay. So let me now take the simplest possible situation where my function f is the identity. So my discriminative function that I had before, that it was f of w transpose x plus w0, is now becomes w transpose x plus w0. So this is what I'm going to discuss from the next 5 minutes, okay? So we're going to take a linear discriminant function, y of x, given by this. So you can think my criterion, I'm going to use this for now to separate, let's say, two classes. So if y of x is positive, is this class. If y of x negative, is another class. All right, so let me define some geometry. And geometry is very essential for data. So, what you see here is my d-dimensional space, and I indicate here only in 2 dimensions as x1 and x2. So the discriminant function, the separating hyperplane will be this red line, all right? Okay, and you see the equation y of x w transpose x plus w0. So I want to tell you a little bit about the geometry. So the first thing I want to tell you is what's the physical meaning of w? So before I do any algebra, can anybody guess what maybe, like geometrically, what w would be? I mean, you know this from geometry, right? When you write the equation of a plane, what is w is going to be? So I had this separating hyperplane that you saw. So what is w? And again, think of the equation of the plane, right? If I write w transpose x equal to a constant, what is w? From geometry. Come on. There's only one choice for w to be. And usually if there's only one choice, that has to be the correct choice. So what's w?
projection?
No. The projection has to be a projection of a point, and here we have infinite x points, so it cannot be the projection. There's only one w. Right?
Slope.
Say it again?
Slope.
Can be the slope, but it's not the slope. What is the opposite to the slope? What's perpendicular to... Well, I mean, they're all related, so it's not the slope. What is it?
Direction.
Say it again?
Direction.
What direction?
The
So
plane.
here's my hyperplane. What direction makes sense? One will be parallel to the plane, right? Which generally will not make sense because if you have a plane, you can find the infinite of those. We only have one w. So which w is that?
Normal.
Normal. All right? Normal. Okay? So w is the vector that is normal to the plane, and you can actually prove this trivially, right? If you take 2 points A and B on the plane, we said y equal to 0 is this line. Okay? So if you take 2 points, and you substitute this as W transpose XA plus W0, and you do the same thing for that, and you subtract these two equations, you get that W transpose XA minus XB equal to 0. And what is XA minus XB is a line, it's a vector on that line. So W has to be perpendicular to the line and in general to the hyperplane. Okay? So remember, W is defines the orientation of the decision surface. Can you tell me, without actually reading, so I don't want you to read, can you tell me what the bias term W0 potentially may tell you, geometrically? Any guess? So we define, okay, so what will you need, right? So we have the normal. So to define the hyperplane, there must be something there that tell us how far this hyperplane is from the origin. Right? I mean, we need that, otherwise we're doomed. So what do you think W0 does? W0 does exactly that, and here is the proof. If you take the projection of the origin to the hyperplane here, and I call this point x, so I can write x, some coefficient, okay, times the unit vector normal to the plane. You agree? And you remember, because this x is on the hyperplane, W transpose x plus W0 equal to 0. So if I take W transpose x plus W0 equal to 0, W transpose W becomes the norm of W squared. So what is alpha? Right? The distance is minus W0 over the norm of W. All right? And if you think that, you take the norm of W to be a unit vector, which makes sense, right? So immediately you can see that the distance from of the origin from the hyperplane is defined by W0. Okay? All right. Now, remember that we said if y is positive, we assign all the points to one class. If y is negative, to another class. So if I take a given point x, all right, you can think of the projection of this point x to the hyperplane, all right? So this is the distance of x from the hyperplane. So in principle, if this distance is positive, you assign it to the class on the top. If this distance is negative, you assign it to the class on the bottom. And the derivation on this slide, basically, which is, I'm not going to go through, there is nothing actually there. You come up with this nice result that says that the distance r of any point from the hyperplane is y of x divided by the norm of w. So you can immediately see, right, that the sign of that r defines what side of the hyperplane you are. Are you in class 1 or in class 2? Okay? I mean, even though I wrote it like that, right, you can see here that this point is of this class 1, but if I give you r equal to minus 0.5, you know the point x has to be on this side. And again, because y greater than 0 is one class, right, class 1, so that the sign of r in that case would be positive, otherwise it would be negative. Okay. All right. So let's make things a little bit interesting. Okay. So let's say we have more than two classes, and we want to use these linear hyperplanes, right? These hyperplanes to separate, let's say, three classes. So if I have three classes, I am going to use two hyperplanes with the spirit that I will use these hyperplanes. That I will use them to separate one class versus the rest of the classes. Right? I emphasize one class versus the rest of the classes. So in this case, it will be class 1 versus class 2 and 3, class 2 versus class 1 and 3, etc. Okay? Or the way it is shown here, class 1 and not class 1, or class 2 and not class 2. So you can see here, with a very simple schematic, let's say I assign this to class 1, okay? Everything below there is not class 1. I do the same thing with class 2, not class 2. So obviously, this region has to be class 3. But then, let's look where the question mark is. What region is that? According to this, it has to be region 1, but according to this hyperplane, it has to be region 2. You cannot have it both ways. So this method doesn't work. All right? So this method 1 versus the rest classifier for multiple classes, it just doesn't work. So we won't be able to use this idea of separating two classes to higher number of classes because it doesn't work. So if 1 versus the rest doesn't work, can you think another mechanism that is not 1 versus the rest that may work? So if you're going to try to separate things, instead of 1 versus the other classes, all the other classes, what can you do? 1 versus?
The other one versus the other one.
Well, the other one is here, all of the other ones.
Not all of the other ones.
So be precise.
1 over the...
1 versus each of the other classes. Okay? So let's do that. 1 versus 1 classifier. So in this case, we're going to need actually 3 separated hyperplanes, not 2 the way we had it. And I give you the general formula here for k classes. So you can see this plane separates class 1 and class 2. This plane separates class 1 and 3. This is 2 and 3. And everything looks nice. You know, this is region 2, 3, 1, etc. But then you're where the question mark is, and there is ambiguity. What are you there, right? I mean, in some sense, this tells you are region 2, all right? But when I look at this, it tells you you're region 1, and this thing tells you you're region 3. So you cannot have it again all the way, so this doesn't work. Okay? Now, obviously, I'm not going to come and tell you that, sorry, you will not be able to classify data in many classes, right? Because then somebody will say it has been zero progress in machine learning. Obviously, there must be some way to do it. Any ideas? And there's no unique way of doing it, but any ideas that you can come with? So remember, for example, in this case, right, for k classes, we needed k minus 1 over 2 discriminant functions, all right, because we have to do this 1 versus 1, so C1 versus C2, C1 versus C3, and then C2 versus C3. What would be a third alternative to do? So if I have k classes, how about if I define k discriminant functions? All right? But if I define k discriminant functions, before I put a slide that has the answer, how am I going to do classification? How am I going to decide if a given region is class 1, let's say? So if I use, so I for 3 classes, I'm going to use 3 discriminant functions. So y1 of x equal w1 transpose x plus w01. W2 of x being W2 transpose x plus W2 0, etc. So 3 functions. So if, let's say, somehow I manage to compute the coefficients with some way, how am I going to do classification if I have 3 functions?
So largest value.
The largest value wins, right? So you compute for a given x, y1 of x, y2 of x, y3 of x. The value that is the largest, you win, okay? And so this is what I have here, all right? So you have k discriminant functions of this form, and the criterion for what class you assign will be based if yk of x is greater than all the other yj's of x for all j's except k. You assign x to ck, okay? And obviously, if you are wondering what are in that case the separating hyperplanes. So if I have a class 1 and class 2, can you tell me what's the equation of the hyperplane separating them? What do you think? So, you know, we said if y of k is greater than all of the other yj's, we assign to class k. So on a boundary between 2 classes, what happens to the 2 y's? Right, if I have class 1 and class 2, y1 of x and y2 of x on the boundary that separates, they're what? They're equal, right? So if they're equal, so I'm writing this for the separating hyperplane of the classes k and j, you can see that the separating surface is it's a hyperplane. It's nice, exactly as we discussed for 2 classes earlier on. As a matter of fact, now you know that if I give you a classification problem for 2 classes, what actually you can do is you can define 1 discriminant function, or you can actually define 2, and both will do the same job. Okay? But this works, right? Obviously, it's computationally more intensive, but this works for any number of classes. Now, there is a technical question that is not irrelevant, right? In this business, everything is relevant. So I said, you know, we split the space, right, depending on this criterion. So let me ask the following unsophisticated or not question. If I use this criterion, is there any guarantee that actually the regions that I will get will be nice regions, or will be regions with holes? Maybe I have a region like that, and then there is another region for class 1 here, and another for class 1 there, and another for, you know, is there any guarantee properties for each of the separating regions? What do you think? I mean, do you expect that these regions will be continuous? I don't want to use the right word because then you will get the answer. But do you expect any nice properties for these regions? I mean, can you imagine that somehow region 1 can be there, but also can be there, and nothing in between? Is that possible? What we will need to prove something nice to show that is not going to happen. We will need to prove that these regions are convex regions. And convex regions, you know what it means in simple terms. If I take a region Rk, and I take 2 points, xa and xb in Rk, and I connect those with a straight line, every point on that line belongs to that region. If that doesn't happen, right, this doesn't look to be something useful to work on. So the answer is actually if you take an x between xa and xb in region k, and you use the fact that this belongs to class k, which means yk of xa is greater than the yj of xa for all j's except k, and you do the same thing for that, you can actually show that this point x bar also belongs to the domain k. Again, if you don't prove this, right, somehow this method doesn't seem to be of any use. But the nice thing is that these regions come to be convex, okay? And so the method basically will work very nicely. Okay. So again, the order of the slides is all over the place, all right? And so the next topic I want to, as we move towards probabilistic models, that I want to discuss, that somehow I can give you the answer now, is not a very good model, is to see if we can use the least squares techniques that we learned for regression, if we can actually use them for classification. And remember, the least squares methods are the same as the maximum likelihood estimate under Gaussian approximations, right? And so we're going to try sort of to see if the same idea may work for classification, but just so you don't worry, the answer is no, it doesn't work very nicely. You should never use it. But I need to do it, okay? So we can learn something from it. So let me do this least squares approximation, maximum likelihood approximation for classification problems. And even though formally we did not do it, we somehow I omitted a little bit the decision making slides. We really discussed that when we did regression, that the solution, basically the least square solutions for a given x, was the posterior mean. If you remember, at each x there was a Gaussian distribution, right? And the regression function was centered at the posterior mean point. Okay. So now, if you have classification and you use least squares, and you classify things to class 1 with probability 1 and to class 2 with probability 0, can you see that this expectation is also the probability of x being in class 1? I mean, if you have a binary variable, right? If you have a binary variable that takes values 1 and 0, the expectation is in the probability that t will be equal to 1 times 1, you know, and the probability will be 0. So the expectation basically would be the same thing as posterior probabilities. So someone would say, this is very nice, right? You know, that's what we want to do in classification. We want to find the probabilities to do assignments to classes. However, we will see that these posterior class probabilities don't look very sensible. And as a matter of fact, you can show that some of these probabilities that you can calculate this way, they are not even in the interval 0 to 1. Okay? So you can actually have weird values coming out of this methodology. So let me build very fast, because we don't want to spend too much time on things that don't work. So we're going to build a regression least squares MLE type of paradigm for classification problems. So we're going to take that we have capital K classes. We're going to use capital K discriminant functions defined like this. I am going to take all of these yks for the given x, put them in a vector y of x, and I can write this equation as, I can actually, merge wk0 with wk by introducing an additional component to the vector x, that I make it equal to 1. You remember in regression, right, we had the bias term, so we can actually put a basis function equal to 1. So I can do the same thing, and I can write all of this together as a vector as w transpose x, where this curly simply implies that I have put together the w0s and the wk's and the one with the x. Okay? So every column of this matrix W is this vector wk that consists from that wk plus wk0. All right? So I'm writing it like that because obviously we want to mimic regression, and in linear regression models this is what we have. Okay? All right. So let me introduce my design metrics. Remember, the design matrix is universal. It doesn't matter if you have regression or classification or anything else. So every row is one data point Excel. Exactly as before, nothing new. Okay? And now my response for each training point xn, my response is a vector tn, all right? So each row of this matrix, capital T, is a vector tn. And what is the form of tn? You remember I have capital K classes. And I do hard assignments, right? So for example, tn can be 0, 1, 0, 0, 0 up to k, or 0, 0, 1, you know, okay? You do a hard assignment of 0 or 1 in the k possibilities you have for the given x, okay? And this is given as part of the training data. So this is the design metrics, this is the response, this is the unknown parameters. So what is the least squares problem? The least squares problem obviously would be to minimize the square error that you do on approximating, these targets, all right, with the regression function, which is W transpose X, okay? And notice I am writing the square error exactly as we did in regression, okay? But I put a trace in because this whole thing, this is a matrix and this is a matrix. And you remember what's a trace for a matrix?
Some like diagonal.
Okay. So here is the sum of everything squared. Because I want to account the errors. I want to account the errors that I do in the approximation, right? And that has to account for the off-diagonal terms also. What I'm saying is it's not only diagonals, right? So when I do xw minus t, the errors will be all over the place. So I want to minimize the error on the 1-1 term and 1-2 term, etc. Right? So the way that I define the trace here, okay, is summation of all the aij squares. Okay? So you can think this as being a summation of all of these error squares for all, for all the elements on the resulting matrix. So when you do the minimization, you get exactly the least squares answer. I will not even bother to repeat it. This is the MLE estimate. It's given by this nice form. Okay, X transpose X inverse, X transpose T, and this whole thing together with a cross. All right, this is the pseudo inverse. All right, so X transpose X inverse, X transpose is what's called the pseudo inverse. Okay, so we. You have to trust me because we have done this for regression. This will be the same solution you will get if you use a Gaussian likelihood, all right, a Gaussian likelihood, okay, and you maximize the log likelihood. Basically, you will get this least squares estimate. Okay. Let me just go back. I'm not going to show you the proof. You remember, if you look at this row, any row of the target matrix T, so every row is everything 0 except one of the capital K elements being 1, right? So that's how every row means. But the bottom line is, if I sum every row, all the elements in every row, the answer is 1. Okay? So actually, there is a proof in the slides that if you have this property for every row basically in the targets, all right? So if the sum of the elements in every row is equal to 1, then you will actually have the same answer for the responses y of x that you get from the discriminant function. Right, so can you imagine if I compute y of, after I finish, right? So let me go back somewhere. So let's say you compute w, you finish everything, and I compute yk equal this times some test point x. You do expect, right, to get, for the assignments of x, most probably you will expect to get 0, 0, 0, 1, 0, 0, 0. That will never happen. So you will not basically get a hard assignment that the point x belongs to class K. It's not going to happen with least squares. However, one property is going to happen that if you sum all of this, the assignments of x to all of the classes, right, you will get a sum equal to 1. So it looks like the total probability is equal to 1, but some of the individual assigned probabilities may be 2.3 minus 1.5. They can be completely ridiculous numbers. The only thing you can say is that the sum, when you assign x to different classes, the sum of these assignments that you get from the discriminant function is equal to 1. Make sense? So basically the idea here is you cannot interpret this as probabilities because you will get in trouble. The only nice property you can say is that somehow if t satisfies the properties that the sum of each row is 1, the same thing you will get with the assignments of x to different classes. Okay, and there is a proof in the notes that actually it's an extremely useful exercise in linear algebra that you may want to read, but really what I summarize is sufficient for us to keep going. All right, I don't need to do this, it's the same as regression. And so let me start giving you some examples. And as I mentioned in these examples for least squares, I'm going to be throwing other methods as well, even though we have not discussed them. All right. So let's see what we have. I have this data first, right? And I want to classify them to two classes. Will you agree that this data, the way, if I look at them, they look linearly separable, right? Easily you can pass a hyperplane, not a unique one, but you can, think of multiple hyperplanes that actually do the job, okay? So if you use least squares, you get this nice blue line, all right? So this is the least square error that you get. Basically, again, like an MLE estimate. This is what you get. So it doesn't look bad. The other method that I will discuss, maybe not tomorrow, maybe tomorrow, I don't know what will fit in the schedule. The other method, you remember I introduced today multiple methods, and I said the first one defines a discriminant function, and it tells you if x belongs to this class or another class. And then there was another method that you assign some function of x directly to this class. You remember that? It was method 2a. So the method that looks the way that I have it here, and I will discuss it again later in the slides, goes with the name logistic regression. And again, bad naming has nothing to do with regression. All right, but it's a classification method. It's called logistic regression. So what it does is you approximate this probability with a sigmoid function of W transpose X. And can somebody tell me why why the function is a sigmoid function and not something else? Exactly, because the output is between 0 and 1. So basically, you can take anything for W transpose X and make it look like a probability. That's a standard trick, by the way. Okay? So that's the sigmoid, that's this logistic regression approximation that you see. And by the way, when you approximate this like that and you compute W, it's going to be complicated on how you compute W. But you can see actually, with this method, can you tell me what is, if I have two classes, what's the equation of the plane that separates the two classes? So this logistic regression defines, with this function, right, defines directly this probability, not Bayes' rule or anything. Can you tell me what is the equation of the boundary that separates class 1 from class 2? So that boundary, how much that probability has to be? 0.5, all right? And the sigmoid is 0.5 when W transpose X equal to 0. That's why even in the logistic regression, you get a linear hyperplane separating the data. All right, so if you do least squares for this particular problem or logistic regression, things look very nice. But I want you to remind me one property of least squares that it was very bad. We mentioned many things, right? We mentioned overfitting, but there was something else about least squares and MLE that I told you never to forget. What was that? Something that has to do with robustness. Anybody remembers? Robustness to what? What's the buzzword that follows?
Outliers.
To outliers. All right. So let's see a simple case. I have the blue data the way you have them there, and now I have some additional points. Would you agree with me, right, that the classifier that I got there, the blue classifier that I got with these squares, perfectly separates this data? Because these data are way too far on the good side of the blue class. So they are in the correct side, very well classified by the blue boundary. However, when you actually try to solve the least squares problem with this data, you can see what happens to the blue line, right? It actually pulls the whole decision boundary way further in a way that actually now you can see that the training data are not classified properly. You have an error actually, you have a misclassification error even for the training data. All right, so even for the training data, the error is not 0. I mean, sometimes that's not a problem, right? Sometimes you may sacrifice some misclassification error so that you can be very predictive on other points, but literally, when you know this is good enough for those points down there, you know, you can see this is not something you would like to see, but this is exactly what happens because least squares basically penalize you, remember, to a square, right? The square error, you remember? So it looks, it's trying to see what the prediction of the function is minus the data points that they are far away. So you know what it does? It takes these points that are well classified, but it makes this square error very high that pulls you basically apart from the correct answer. Okay. So here is, so I mentioned the logistic regression. So the logistic regression is very good to separate the classes. So you may say, how least squares will do if I have 3 classes, right? And you can see, I don't know what the colors here, but I see 3 sets of points, all right? And you can see there is the least squares doesn't give you actually a perfect answer. Sort of it comes up with 2 hyperplanes, but there is a bunch of points that you can see here in the middle. They're misclassified, okay? But this is what you get with least squares. Now, you can actually generalize the logistic regression function, right? This, let me just put it again so you remember. Remember the logistic regression? You postulate directly this to be a sigmoid of W transpose X. Now, you cannot do this when you have 3 classes. So when you have 3 classes, what will you do? Instead of the sigmoid, you need to use something else. And again, I will do this in detail because we have to derive for those problems with W's. There's something else here. So, you know, if you have a point X, and here it shows phi of X, but it doesn't matter. If you have a point X, you assign it to the class that has the maximum of these probabilities. And these probabilities are bounded by this function. All right? So you have sort of 3 discriminant functions, but you define these probabilities with this nice normalized exponential function. And what's the name of the function? I mean, we will see it later on. It's a very famous function in machine learning for multi-class problems. So the logistic one, and what is this? So we know the names. This function, what's the name of it? Softmax. Softmax means it's a soft version of the max function. Okay? And if you want, you can visit the slides to see from where the name comes and why this approximates the max function, but it's called a softmax function. So effectively what you do is, right, for 3 classes, you postulate 3 alpha k's, okay? And now you need to make 3 probability models. I mean, that's the whole idea, right? You need, so basically, if I write down the probability of X belonging to class C1, C2, and C3, I want to be sure that those things are between 0 and 1. And what else we want to be sure? That if we sum them, right, will be equal to 1. And this function, the softmax function, does that. So anyways, if you I still call this logistic regression because it's generalization to multi-classes, but you can see how nicely this softmax is able to define two hyperplanes that separates the data with actually zero misclassification error. Okay? So least squares doesn't work for this problem. You can actually play on this particular data set here for the least squares, and it took me some time long ago to actually clearly mark all the regions. But if you come up with, you compute the W's for each of the discriminant functions, yj, and then you can identify for each x which function y is the highest, and that's exactly what I'm doing here. For example, here y1 is less than y2, y2 is less than y3. Everything is less than y3, so this class here is 3, and you can see all the regions marked carefully for this particular case. Okay? All right. All right, there is nothing more to add on this, okay? All right. 126. Let me do the following thing, actually. We have 15 minutes, and I want to do something more useful, probabilistically speaking. So let me go to slide 59, right? So let me talk a little bit in the remaining 15 minutes or so. Let me talk about probabilistic generative models. And you remember, in the generative models, you need to calculate the probability of ck given x by calculating the class conditional probability, p of x given ck, and also by having some prior models. Okay? So you have to use these generative models, you have to know what this probability is. Okay? And you need to know the prior, and then you have to use Bayes' rule to come up with the probability of x being in class C1. And when I say you have to know, obviously you're going to have to, if I go and I assume, let's say, this distribution to be a Gaussian, somehow I'm going to have to use my training data to calculate the mean and the variance. I mean, we're not arbitrarily going to assume what those classes are. We're actually going to use, let's say, maximal likelihood estimation to compute these probabilities. Okay. Follow me now in the algebra and look at this equation up to this point, and tell me if you have any issues, right? What you see on the denominator is just the normalizing factor in the Bayes rule. Just be comfortable that this equation makes sense to you. Okay? Right? Don't pay attention to the second part or anything like that, but we agree that this is just Bayes' rule, okay? So we call it again, this is a generative model because it requires that, let's say for class 1, we need to know how the data are generated. So we're going to have to make some assumptions that is some Gaussian, let's say, with some mean and variance that somehow we're going to have to compute. And obviously to calculate the normalizing factor, we're going to have to do the same thing for this. And also we're going to have to calculate the primes. Now I want to do a trick to show you how, even though this is a generative model, somehow we can take the form of a discriminative model, which reminds us exactly the logistic regression model that I showed you before a few slides ago. So what is the trick? Let me define A to be the log of this ratio. Okay? So A is the log of P of x given C1 is C1 divided by that. I'm not telling you what A is, I just call this A. Okay? Can you actually see if you divide here by this term, all right? Can you see immediately that what you're going to get is e to the A divided by e to the A plus 1, which is equal to that? And if you know the equation for the sigmoid function, can you immediately see that what you actually get is a sigmoid function in A? Wow, that's interesting. Now, this is by cooking up, right, what I defined as A. right? So literally what I cooked up, I said I'm going to call this A, but somehow at the end of the day, all right, at the end of the day, this model looks like the logistic regression model, but of course, it all depends what A is. Because in the logistic regression model, A was what function of X? In the logistic regression, what did I have for A? Remember, let me go back. No, now back, it would be 50 slides back. So what was for the logistic regression? What I had sigma of A. What was A? W transpose X, that's it. Okay? So now, will I actually be getting, when I do this log, right, under some assumptions, will I get W transpose X? If I do, then this looks like a logistic regression model. So can you guess? So if I take this to be a Gaussian distribution and this to be a Gaussian distribution, can you imagine situation to get W transpose X for A? You know what it means? That the quadratic terms in the Gaussian, when I take the logs, have to disappear. Right? So for the quadratic terms to disappear, can you guess, looking at this ratio, what assumption do I need to make for the two conditional class distributions? Use your imagination, right? Because you have log and log, right? So when you look at the quadratic, to get something that is linear in X, how the quadratic is going to disappear? The quadratic term, right, how does it come in the Gaussian? It comes, X transpose times sigma minus 1 times X. So what will make those terms to disappear in this definition?
Same variance.
The same variance. So in that case, the variance will cancel and we will get basically linear decision boundaries, and it will make the model to look like a logistic regression model. But remember, it is much richer than logistic regression model because you can produce data for class 1, data for class 2, right? This contains way too much information. The logistic regression model tells you directly this is some function, sigmoid function of some linear function of X. That's it. Here, you can make it look like logistic, but there is much more information than the final answer. So let's see fast these results. First, I want to show you the logistic regression function, how it looks like, right? So we said you can take anything and you can squeeze it with a logistic regression, and you can generate probabilities from 0 to 1. So you can use this for any problem. If you compute something as a function of X, you want to make it to produce a probability, always pass it through a sigmoid. Now, the sigmoid, when it comes to actually doing algebra, it's painful. Okay? The algebra is a little bit painful. And often, the sigmoid is approximated by what is called scale inverse probit function. Okay, so when we do algebra, and actually I may need this as early as tomorrow in the lecture, when we do MLE for the logistic sigmoid model. So you fit the logistic function with what's called scale inverse probit function. The name doesn't mean anything. Here is the definition of the scale inverse probit function. This is the standard normal, all right? You integrate it from minus infinity to lambda a, and that basically gives you the cumulative function calculated at lambda a, and this is what is plotted here for a value of lambda that is square root of pi over 8. Can you actually guess, looking at the picture, how lambda was computed to make this to work? Just looking at the two pictures. I mean, I'm guessing now, right? So you have to guess with me. So obviously, this is a general definition. Then I told you, take this lambda to be square root of pi over 8. So I'm asking you how that square root of pi over 8 came about. Look at the picture. the two functions have been made to do what? At alpha equal to 0. Obviously, they will give you the same value, but here there is something else they give you at that value.
Same slope.
The same slope. So that's exactly how that, so there's no magic here, okay? So the calculation is very simple, and I believe it's actually, the proof is given in the slides, but I want you to remember that if you want to do algebra with, so if you want to calculate derivatives of the logistic sigmoid, look immediately how trivial it is, right? You're going to have to calculate derivatives of this, which effectively will lead you to a Gaussian. Right? So no algebra, no nothing. So it's already there. Okay. So just inside parentheses, because this will come up in the lectures as well. If you take the inverse of the logistic function, you get what's called the logit function. Is log of sigma divided by 1 minus sigma, and in this case looks like that. Okay. All right. So before I start giving you results, in the case at least of the same covariance for the two class conditional probabilities, let me just say you can actually generalize this model to arbitrary number of classes, but instead of using the logistic sigmoid, you have to use the softmax function. So effectively, this is what we got with Bayes' rule, right? That's the first two terms here. So you're going to write this as e to the alpha k divided by this summation, where now my alpha k is not going to be the log of two ratios. My alpha k is going to be the log of this conditional distribution times the prior. And actually, if I remember, either in Bishop's book or in Murphy's book, the final answers are correct, but I think some of the intermediate equations, they had some mistakes, okay? So you can actually write this as that, where alpha k is given by this nice formula, okay? And obviously, this works because if I sum for a given x all these probabilities, you will get equal to 1, right? And e to the alpha k divided by that summation is always between 0 and 1. So it squeezes basically the results to a probability space from 0 to 1. Okay, so let me show you now for the logistic case what happens in the calculation of that alpha. So I'm going to take a class conditional probability to be a Gaussian with this mean, and you notice the mean I make it to be class dependent, but the variance now, there's no k subscript, so I'm taking the variance to be the same. So remember, this is the model, all right? Alpha of x is this log. So I, yada, 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 you plug in the logs of the Gaussian, etc., you continue. The squares, the x transpose sigma inverse x cancel, and what you get is that alpha of x is this times x plus a constant, which is basically our exactly what we had for the logistic regression model. Okay, so somehow by canceling the quadratic terms, we get a separating now hyperplane that's linear, right? W transpose x plus W0. And what is interesting actually is that these prior probabilities of its class only affect W0. And remind me, W0 is what geometrically?
Distance.
It's the distance of the hyperplane from the origin. So in some sense, it's not even that significant, right? Because you can shift this lots of times, right? There's no unique thing. So you can shift it in parallel, and it doesn't make a big difference, which is nice. But you can see that the vector W requires mu1 and sigma. And remember, I have not said a word yet. How do you compute mu k and how do you compute sigma? None of the above yet. Okay? So they're all unknowns, but if somehow we knew them, this is how it looks like. All right, so if you actually use this model to separate two classes, I am going to give you first the class conditional probability. So this is a red Gaussian that generates data in class 1. This is a blue Gaussian that generates data in class 2. Now, when I squeeze this, when I compute W and I pass this to the sigmoid, with this W here, I get the posteriors, and you can actually see the posterior of sigma 1 given x, and the posterior of sigma 2 given x. And actually, even though I'm color blind, I can actually see, can you see that the assignments here are soft assignments, right? Because you compute probabilities. So there is a continuation of the coloring from red to blue. And by the way, I recommend that you start learning how to actually plot things that even at a given pixel, you have 30% of red, 20% of blue, because this is the only way you can show posterior probabilities. Okay? So this is very nice. Okay, so we actually, now if somehow we can actually compute those, right? And obviously they have been done this in this particular case, you can compute these posteriors and we're done. Okay. So in the case for classes more than 2, all right, so you can actually, alpha k will have a quadratic term because we don't take a ratio, and a linear term and a constant term, but somehow when you have e to the alpha k's, right, and then you have e to the alpha j's, this term will be common to all of them, so it cancels out. Right, so what actually you're left is only the linear terms. So the alpha k's eventually in the equations, okay? I mean, in some sense, right, I cited before, I wrote alpha k for this model to be this times that plus that. I did not put this term because this term will cancel out. So in some way I should go and call this alpha k prime. But why bother? Because at the end of the day, right, if you write a model like this, keeping these terms, it does the job. All right. And that's what I have here, okay? All right. Another example with 3 classes using the softmax function. And I want you to look first on this picture and tell me why 2 of the boundaries look to be like quadratic. The zigzagging is only plotting issue. And this boundary looks to be a straight line. What does that imply? So let's say this is class 1 and this is class 2. What do you think happens between class 1 and 2? Classes 1 and 2. To get a straight boundary here, what do you think happens? When do we get, remember we get linear hyperplanes, I mentioned it before, right? To get W transpose X plus constant, you know, requires something to cancel. What's that something? The variance will be the same. So this class here and that class need to have the same variance. And obviously, this class and that class and this class and that class, they have different variances. That's why you get the quadratic terms. Okay? All right. It's 143, right? And I cannot do the algebra, but can you imagine what would be the easiest way to actually compute the mean and the variance for these models, given some training data? What do you think would be the approach? The easiest. So we have training data, right? And we said this belongs to this class, this belongs, so they're labeled data. I give you training data, and I give you the x's, and I tell you what class they are. All right? So what would be the easiest way to actually assign, compute the parameters in these class conditional models and also the priors? The easiest model. Point estimate. What would be the easiest point estimate? How many point estimates you know? Okay, what's the first one? MLE. So what we have to do is we have to do an MLE. So we actually have to write the joint probability of the data, right? So the probability that the data point generated by class 1. First it has to be in class 1, which is a prior times this probability to power Tn, because if it's in class 1, Tn is equal to 1, otherwise it's 0. Take the logs, and then start taking derivatives with respect to mu1 and mu2, and then start taking derivatives with respect to C. We will do the algebra tomorrow, and you'll be surprised that the results come to be exactly what someone could have write down by hand without any algebra. So the results basically come to be the common sense results. Okay? And so we will do that tomorrow.